Next one is like grouping, associative law. Okay, we change the way we group the statements. Okay, the result still the same for OR operation and operation. Okay, the next one, distributive law. This proposition can be expanded out like this, right? P or Q and with P or R. Okay. And the last one is De Morgan. Not sure if this is a new one. Have you seen De Morgan law? Okay. Not of P and Q would be not P or, change and to be or, and the not would be for both P and Q, right? Not P or not Q. Similarly, instead of and we have or, then we switch the sign, or to be and the not would be for both P and for Q. Okay. A little bit more. Based on the laws that we have discussed, we can obtain the following form. Okay, like P or not P is true, always. P and not P is always false. And if we have a lot of propositions, like n of them, we can still find out if the statement is equivalent or is true or false, right? Doesn't matter how many terms we have. Okay, let's see a couple examples from the textbook. Example number 5 and 6. Show that these two statements are equivalent. Okay, how can we do it? Instead of using a truth table, we should be able to apply the laws, Boolean logic laws, okay, to find out the answer by starting with one of them, okay, and work on the statement using the laws until we get the same match as, or same or not same as the other one. See if they are equivalent or not. Okay. So there are many ways to do, right? Depending on, like, if you like to apply which law first, something like that, the way you derive the statement. Like in this text, they first use De Morgan law to change, right, this one or to be and then they use De Morgan for the inner term, this part, right, not P, so we have this and change the sign and to be or, Q would be not Q. Okay, and after that simplify the term, because we know that double negative, this one would be equal to P, right? After that we use distributive laws, okay, and then we can simplify the expression. Okay, we should be able to do that. Next example. Example 6. To prove that this statement is a tautology, always true. Okay. What does it mean? If this P and Q is true, this second statement must be true, right? So it means that they have to be logically equivalent. Next section. Predicates and quantifiers. Definition. Predicate is a property of the object, okay, that the subject of the statement can have. For example, the statement x is greater than 3. Okay, x would be the subject. The property of the x is greater than 3. So greater than 3 would be the predicate. Okay, according to the definition. If we have, if px is equal to x greater than 3, okay, p would be the subject, okay, and greater than 3 is the predicate. X is a variable, okay, because px is like a function of x. To get more understanding of what it is, let's see some examples. First one. If we have function px, okay, when x is greater than 3, what would be the truth value of P4 and P2? Right? We can find out. The statement says that Px, when x must be greater than 3, so P4, 4 must be the x, right? So we check if 4 is greater than 3. If it is true, right? P2 means that x is equal to 2, which would be false because the statement says x has to be greater than 3. Okay? So P4 is true and P2 is false. Right? Okay. The next one with two variables, x and y. The statement is x is equal to y plus 3. No, just only P4. Right. They ask for each of them, not both and. Okay. If it's compound statement P4 and P2, that would be false. Right. Next one, x equal to y plus 3. What would be the truth value of Q? 1, 2. Means that x is equal to 1, y is equal to 2. Is that right? Plug into this